Okay, I 100% lost the beginning part of this video, so I'm going to start here and then go back and record the first part and post it, because at this point I'm disheartened and don't want to restart from the beginning. So here we go. I've got chi-square with equal proportions, I've got some cards, and what I'm going to do is I am going to go ahead and draw a random sample of cards. So I want 40 cards. Woohoo! And yeah, we're going to see if we get an equal sampling of the suits. So how many clubs do we got? 1, 2, 3, 4, 5, 6, 7. I'm making you watch this the last time I paused. It screwed up. 8, 9, 10, 11. Looks like I have 11 clubs. I need diamonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and that's about it. Wow. Alright. Time for some hearts. Have a heart. There's no hearts in the first row. 1, 2, 3, 4, 5, 6, 7, 8. Interesting. So if all goes well, I should have 10 spades? I hope. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, cool. I got it right the first time because I drew 40 cards. This should add up to 40. Perfect. Let's do this. Come on. Why is it being weird? Okay. So let's set up our null and alternative hypothesis. I think my suits are going to be equally represented. So in here I'm going to state the suits all have the same proportion of 0.25. Ta-da! Alternatively, at least one suit does not have a proportion of 0.25. Now it might be 2 of them, might be 3 of them, might be all 4 of them are not right, but there's only one way to find out. So you can actually calculate the expecteds from this, since you know the total sample size was 40 cards, and you know that the proportion that your hoe is asserting that it will have is 25% for each of them. That means the expected count should be 25% of 40, which is just 10 for all of them, since they are assumed to be equally proportionate. Let's go throw this into Minitab. So goodbye cards. All this stuff is on the other video. So here I'm going to have suits, and I'm going to call this counts because I need to name it something different than the others. So I have diamond, club, heart, and then spade. Perfect. And these are gotta, oh wait, I need my sample. Where is it? Up here. There it is. 11, 11, 8, and 10. Beautimus. Okay, let's go ahead and have Minitab calculate our test statistic and associated p-value. So once again, we're going to be going up to tables. We're going to choose the chi-square goodness of fit test. And this time, I'm going to tell it once again, I have summarized data in a column. So my observed counts, that would be what I called counts. My category names are the suits. And it defaults to equal proportions, and I actually want that this time because I want these to be all the same. I'm just looking for, is there a difference in one of these or more? Let's hit OK. And there's our goodness of fit test. Okay, cool. So our test statistic is showing up right here. Notice if you were questioning whether or not you were correct with your expecteds, they show up right here. Contributions to chi are kind of small, which is interesting, which means they're not that far off. Looking at your chi-square test statistic, it's only 0.6, so that's what we're going to report in D. And then our p-value is enormous because, well, our test statistic was small. A small value of chi, usually it indicates that you're not going to have a big p-value. So there we go. Alrighty. State your conclusion. Well, with a p that big, there's no way I'm rejecting that null hypothesis. So the evidence suggests that the card suits are all equally proportionate. Yay, which means no suit is represented more than the other, or your deck is fair. Good times in fairness land. Let's talk about some chocolate. So I'm going to hit enter a couple times and put this on the next page. Take a drink on camera, because that'll go well. Ooh, it's nice and cold and refreshing. Ooh, this is killing my voice slowly. All right. So, in case you didn't know, people like chocolate. So I have chocolate preference as a variable all in one column over here in C2. And then I also have gender, but we're not going to be using the gender variable at all. We're just going to ask ourselves, does this match what we found out? So after doing some digging on the internet, I noticed that Ghirardelli had some information about what was popular based on their sales. Now, this data is taken just from a random sample, so it might not match Ghirardelli's sales, and we're going to find that out right now. So 15% of individuals prefer dark chocolate, 80% prefer milk chocolate, and 5% prefer white chocolate. Gross. Let's see if there's any difference here as to what Ghirardelli claims. So for this one, since there's only 3 groups, I think I'm just going to do my hoe is like P for, you know, dark is 0.15, P for milk is very large, and then P for white is uber small. Okay. And then for my ha, at least one proportion is not as Ghirardelli claimed. Let's see if I can spell Ghirardelli right the first time. There's another R in there somewhere. Ghirardelli. Ghirardello. See? I can't do it. It's fine. Spell check. So, since I have my data in a big column right here, I'm going to need Minitab to do both the observed and the expected for me and produce the test statistics. So I'm going to have it do all of it today. It's going to do all the things. Let's go to tables. We're going to choose the goodness of fit test. Yay. Categorical data in a column? Yes, it is. It's in the preference column. And then it's not equally proportionate. I got to have you're going to use the ones that Ghirardelli gave me. So notice it reordered this, so I got to be careful. Dark is 15%. Or no, it didn't. It's exactly in the order I thought it was going to be. It's 80, and then white on the bottom. You really got to be careful and watch for that, because it does it quite at random. And that's it. We good to go. Let's hit OK. I linger on that screen on purpose to give you guys some time. Cool. So that's interesting. There's 400 people in this sample. I didn't even know that. Here's our observeds. Let's type those into our box. This is also really typical of some of the questions you're going to see in your homework. 114, 83, and so for total we had 400. Yep. And then for my expecteds, I'm going to grab that from the expected column. So 60, 320. Ooh, we're going to be really far off. I can just feel it. And 20. Those are not even close out of 400. All right. So hopefully you're looking at those contributions to chi and seeing that they're all huge. So the p-value for this test and the test statistic come out absolutely enormous. There's no fixing it. Very large. Very, very large. Yep. This is one of the biggest chi-square values I've ever seen. That's what I get for getting information off the internet, I guess. Once again, p-value is so small, it's not going to be willing to report it. So it's teeny, teeny, teeny. So when your p-value is really, really teeny, it's definitely going to be less than 5%. That always means you're going to be rejecting your null hypothesis. Boy, I'm having a hard time with the t's today. So since I'm rejecting my null hypothesis, there is evidence that all of the proportions are different from Ghirardelli's claim. Evidence suggests that, and I know it's all of them because looking at the contributions to chi, all of the contributions are large. Yep. That, let's go with none of the proportions. Yeah, everybody different. Interesting. Very interesting. Okay, I told you I'm going to record this one backwards because I lost the beginning of this recording. So we're going to back up and we're going to redo the beginning of this. Should be a good time. So earlier I calculated some p-values, as you can see. We're just going to pretend that didn't happen. Ay, ay, ay. This is the worst video ever. So it is, if you remember back to the beginning of the lessons, you'll notice that I said, oh, we'll use Minitab to calculate the p-value, we'll use Minitab to calculate the critical values. Here's how you would do that. So if you go to probability distribution plot and select display probability, you're going to change this to a chi-square, because we're dealing with chi. You're going to put in your degrees of freedom of 3. And then in this case, I know the value of chi, so I know a value on the distribution. I'm going to choose x value. And then I'm going to type in the value of 4.467 and hit OK. So this is how you can get a p-value if you need it and it's not given to you. So notice in some of the examples I just did, I didn't have the p-value. I had to go get it, which kind of stunk. Oh well, what are you going to do? Anyway, let's do this next one. So remember, if you're doing lots of values in a row, you can click the Make Similar button to do the same thing a second time. So I'm going to need to change my degrees of freedom to 13 and my chi value to 11.87 and then hit OK. And you notice that this one is much larger than the one you have seen previously because, well, they're closer together. One of the ways that you know that you're going to end up with something that's kind of large is that if you have a chi-square value that's within 2 of your degrees of freedom, 2 less than degrees of freedom is about where the peak occurs, so where that mode occurs in the chi-square distribution. And since we're always doing right, I know that if I'm close to that, like these are, it's going to be pretty big. Now, if this was something like 14, or even like 15 or 16, I'd be like, okay, maybe that'd be pretty small because that's probably going to be out here and get rejected possibly. Anyway, let's look at how to find a critical value. So you'll notice that in the notes, I was finding values of chi and then comparing them to my test statistic, and then I would just use that to decide should I reject or fail to reject. Here's how you do that. So if you have the degrees of freedom and know your alpha, your level of significance, or when you're going to cut off a chi-square value as being something that's significant evidence against the null hypothesis, you're going to use this. So we're going to go to, once again, probability distribution plot, display probability. I'm going to click on the normal and change it to chi. My degrees of freedom for C is 3. And in this case, I know alpha. I know the probability, so I'm going to change it to probability. It defaults to probability. I forgot that. I'm going to use 0.05. Remember that chi is always a right-tailed test. So you notice I'm only using right tail. I'm not touching anything else. I don't change it at all. So I'm going to hit OK. And there we go. So that's where that 7.8147 came from. And you would use this to make your decision. You would then take your observed and your expected values, subtract them from each other, square those, and then divide by the expecteds and add all those fractions up and then see what you get. So if you got a chi value from the test statistic that was like over here, so it was larger than 7.8147, you would be rejecting that value. So how you'd make that decision is if your test statistic was greater than 7.8147, then you would be rejecting the null hypothesis. Now, if it was the other way around, so just like I have below, if it was smaller than the 7.8147, then you would be failing to reject. Let's calculate the one for D so you can see where I got that number from. So I'm going to hit Make Similar again since I'm doing the same idea. I'm going to change my degrees of freedom to 9. And my value for alpha here is smaller too. It's 1%, another common value of alpha, but most of the time you're going to be using 5. We're going to hit OK. And that's where the 21.666 came from. Scary. I should have known when I got that answer that Snagit was going to screw up and delete my recording. How did I not know? Darn. Okay. Let's do a typical goodness of fit test. So a real estate agent is located in a metropolitan area in the northeastern United States. They keep data on various types of properties and purchased in the area. Historically, 15% of purchases were condos, 30% were townhouses, 40% were single-family homes, 10% were commercial properties, and 5% were land. With changing demographics, the agency was wondering if the current distribution matches historical distributions. This is an incredibly common use of the goodness of fit test. Does the current result match history? I've got a bunch of data backlogged from years and years and years ago. We want to know, has anything changed? So you'll notice that I took this table of values here, and I made note of this in the video that didn't record, that anytime Minitab is being used, you're going to have to take your variables and represent them vertically, which I've done over here. They have to go upsy downsy or else it's not going to work. Now you can get around this a little bit. You'll see that in the second video where I use it to do a table, and it's the only time you can really do a table like that. So you want to do them upsy downsy for the goodness of fit. And the other thing you want to notice is I'm really comparing data to itself. I only really have one variable here, type of property, and I'm just comparing it at 2 different times. So this feels like the paired test, I hope, to you, but like the categorical version, because like categories and stuff, not quantitative data. In particular, I wrote 2 different versions of the null hypothesis. You don't have to write 2. I wrote 2 so you could see the 2 different ways you could write this. You could write that the current proportions for the types of properties match history. It's the same as what it used to be because HOs have to be statements about sameness or equality. That's just how they roll. And then my null hypothesis could also be written with like, okay, well, condos are 15%, townhomes are 30%. Homes are 40% and condominiums are 10%, land is 5%. This is just saying if I look at the proportions nowadays, it matches what it used to be. If I look at the proportion nowadays, it matches what it used to be. So it's saying the same thing, but just writing it in more of a mathy sense. And the alternative hypothesis, we really only write one way, and that's that at least one of them is different. Now I don't necessarily know which one is different. I just, know that one of them must be different. Let's go ahead and perform this test so you can see how it's done. So to do this, we go up to Tables. We're going to choose the Goodness of Fit test. All right, once again, I have my data in a summarized table, so I want to click on that. I've got to put my observed counts in there, and that for me is the frequency. Since I'm doing the housing, I'm always going to want to have the category names there, so I'm going to go ahead and click in Type. Now I want to change this from equal proportions to specified proportions because I have values right here that I'm going to be using. And I've got to be careful here. It brings up commercial first because it likes to alphabetize this. So be careful. The 10% is going first because that's commercial. Condos were 15%. Homes were 40%. Land was only 5%. Ooh la la. And then townhomes was 30%. So be careful when you're typing this in. It likes to change the order of things. And now we're ready to go. Let's go ahead and hit OK. There we go. Okay, so there's a couple different things going on here. Notice there's your observeds that we had from the raw data that we were given from the sample the real estate people did. And then we've got our proportions from history. And then we have our expected. So how it came up with the expecteds is it took the total in the sample, the 325 that are in adding all these up. If you add these all up, you'll get 325. And then it multiplied it by the proportion. So if you take 325 and multiply it by 40%, you'll get 130. Got it? And then you got to do that for all these proportions. 15% is that, 30% is that, da, 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 da. So these are the expected counts. Then from that, we can also get the contributions to chi. So these are the fractions you would get if you did the next step by hand. So if you took 78, subtracted 130, squared it, and then divided it by 130, you would get 20.8. You do that for all of these, you get the following. You add all these up, and you get the chi-square test statistic, that's 62.54, which, yields a p-value that's super small and is going to tell us to reject the HO. That's not the important part. What's important with this is notice 2 of your chi-square values are enormous compared to everybody else. That tells you that the ones that have the biggest difference are actually condos and homes. Those are the ones that had their sales change significantly. Look for the large ones. Ones that are like 1 or 5 don't mean anything. Anyway, so looking at this table, looking at this chart, you have a way of comparing and seeing what's actually happening. So for those of you who are colorblind, the first bar for a condo represents the expected and the blue represents the observed. So expected is your history, blue is what you got in the sample. So from this you can say, oh, it looks like currently condos are actually up in sales. And then looking over at homes, the expected is much larger than what actually sold, which means homes are down, condos are up, man. We're able to see the change. And then commercial, land, and townhome, they're not a significant difference, and you know that by, looking back at the contributions to chi. They're just not big enough for it to matter. So looking down at writing our conclusion, we'd say, yes, our p-value is small. I'm going to reject the HO. It looks like some of the proportions are different, and specifically the sales of condos, I should say this better, the sales of condos are up, And the sales of homes are down significantly. Oh yeah, that's better. I like it. Good times. I hope you've enjoyed this video and that it's helped you understand some chi-square testing, and I look forward to seeing you in the next one.